where the breach occurred. Okay, so these were all goals. Not going to say that we achieved all of them, but we got most of them. This is an illustration that shows you the design, the 3D design. There were over 2,540 energy source points, 2,651 receiver points, which netted 6.6 million traces. Now, these are like slices through the earth. Of those, 48,960 were processed and pulled into bundles, if you will, to create the 37.5-foot bin spacing. Now, I'm not a geophysicist. I probably said some things that were a little off, but
You're not saying.
thank you. I appreciate your guidance.
Somebody needs to guide
Processing, as I said, resulted in this 37.5 feet of bin spacing. Now, this is where it's going to get a little touchy, but I'm just going to tell you what we found. And everything that we've done in this recovery has been guided by science. It's been guided by fact. We don't like conjecture. We don't like speculation. We don't like conceptual models. And here's a case where the 3D data, as processed by Kevin Hill, depicts the same area that was depicted in the conceptual model early on in this process. Now, with all due respect, conceptual models are absolutely necessary before you have the data. It's a concept. It's what we have to go by. It's what we start with. But in the process of building a case, we gather data, and we look for answers. We look for solutions. We look for signs that can either verify the concept or point in some other direction that gives us more clarity. And what you can see from this interpretation is that the boundary of the salt, as reflected by the termination, I'm trying to get this working. Okay. Now what a geophysicist does is he looks for reflectors. And where there's a boundary that he's trying to identify, he looks for the termination of those reflectors. And so what was possible from Kevin's work, he was able to identify the edge of the salt. From this area up, and you can see the boundary, see the overhang. Kevin was also able to image the sinkhole in the subsurface. You see a very distinct area about 400 feet deep that is of disturbed reflectors. In other words, there's no continuity. You can see reflectors on one side, they break up here in the sinkhole, and then they move across to the east, and they're undisturbed. Now, as you look beneath the sinkhole, close to the edge of the salt, these reflectors appear unchanged. And so the first conclusion that we came to was that there doesn't appear to be a massive collapse zone underneath the sinkhole. The data tells us this. The second point that we were interested in was identifying any potential large void spaces that could lead to another dramatic event. You'll recall that early on in this, there were questions as to whether or not another sinkhole could develop, independent of this hole. And so there was legitimate concerns as to what was driving this process. So there was a serious, very serious attempt to look for any void spaces in that strata, in that section there. None were found, all the way down to the cavern nipple, which is right here. A third primary objective, Kevin, was to search for hydrocarbon traps, hydrocarbon voids, the indication of any concentrations of oil and gas that might be lurking in the background that could eventually find their way to the surface. None were found. None. In fact, the big hump, which was readily apparent, very distinct, in the 2007 3D seismic survey, was gone. No sign of it. This is what we're dealing with. This volume of hydrocarbons in an aquifer that contains gas. We do not see any large voids. We do not see any large hydrocarbon traps along this column. What we see is almost a funnel, small, relatively small area of collapsed strata and a very tight contact between the salt and the apparently undisturbed strata outside the salt.
Can I ask a clarifying question?
Go ahead, Bob.
Is it Mr. Hill's conclusion and Texas Brine's conclusion that all of the gas that we have to be concerned about has now moved into the aquifer?
No.
Is it Kevin's?
Is that your conclusion?
That is a possibility.
Oh,
That's a possibility. It's a logical conclusion to make based upon what we've seen in the data. Okay, if there were other hydrocarbon zones that are apparent today from this data that didn't exist in 2007, then we could conclude that maybe gas was redistributed from the big hump. From what we see here today, the big hump is depleted. It's gone, and we do have signs from the 3D of gas up in the aquifer. And that's what we are pursuing with the relief wells. Okay? Now another major piece of information that we were after from this 3D seismic was to supplement the vertical seismic profiles that we did to verify cavern 1's proximity to the edge of the salt. And with so much resolution, we were able to do that. And Kevin is confident now that we have approximately 150 feet of space between the edge of the dome and the nearest boundary of the salt. Okay? And as Bruce mentioned, and I'll wrap up with this last comment, we still have a lot of work going on. Kevin is not through yet. He's still processing the 3D to try to get more resolution of the gas that's in the aquifer. And because we had some gaps in the 3D, some areas that we couldn't get imaging of, we've elected to go with this electromagnetic tool that will actually be flying over this Friday. And we hope that that will close the gap in some of these areas and help us actually better characterize the aquifer. If we know the aquifer, if we know the highs and the lows, and as much as we can about it, we can be much more proficient and sufficient in going in and recovering hydrocarbons. So, with that, I want to turn it over to Dr. Goodman. He's going to talk a little bit about this process, and Bill is also going to explain to you some of the things that are currently going on in the background under his leadership to help characterize the aquifer.
Thank you, Mark. Good evening, everybody. My name is Bill Goodman. I'm with Respec. Texas Brine asked me to coordinate a group of the experts that they've retained over time to really focus some energy and attention on the shallow subsurface, where we have the gas now. You can see on the seismic profiles that the sinkhole and the aquifer systems are a really thin part up at the top. But really, in essence, it's a really important part. So we need to expand that understanding of that really narrow interval. Let's say the alluvial aquifer system that includes the MRAA is something on the order of the top 600 feet of the subsurface. And that's the sand layers and the clay layers that comprise that alluvial aquifer system. So we pulled together experts in geology, hydrogeology, geophysics, isotope geochemistry for the gas, water quality. We have a petrophysicist who understands the reservoirs, and we have a world-class geotechnical engineer. Half of the experts on this are PhDs, so we have sort of a peer group to the Blue Ribbon Committee, right? What we're going to do is focus all of our energy on the shallow subsurface condition with the goal of really trying to understand that interval of the geology well enough that we can determine where the gas is and how to most effectively and efficiently get it out. So part of that is trying to get better imaging. The seismic data are good, but as we can see, when you're imaging to 10,000 feet, it's difficult to get a very clear image of the upper 200 feet or so. In order to do that, we have to do a different type of geophysics, and this will start happening real soon, possibly in a couple of days. Right? We've retained a firm called Fugro. They're internationally renowned. I think the outfit that's going to do this type of aerial survey for us is based in Ontario, Canada. Right? And you can see a helicopter-based aerial survey. It's called an EM survey. What it does, by looking at the electrical properties of the soils, they'll be able to tell us the lateral and vertical distribution of sands and clays in that upper 200 feet of the subsurface where we don't have a real clear image from the seismic data. The whole purpose of doing this is that we can build maps that are more precise than we can by connecting the dots with wells alone. So, for example, up on the upper panel of this diagram, let's just say that all of those different colored dots are wells that go into the top of the MRAA or some other horizon, right? And the colors represent different types of sediment, whether they be sand or silt or clay. The geologist, when he's working only with well control, has to basically contour those data out or connect the dots or sort of make an educated guess in between them. With this type of survey that we're talking about here, this EM survey that Fugro will do in the next couple of days, the electromagnetic properties of the sediments are going to basically tell us where the sands are and where the clays are. For example, in the lower panel, the greens and yellows would be sands, right? So that way, if we know what the geometry of the units are that may be holding the gas, well, the odds are that we're going to be able to use the venting wells a lot more efficiently and effectively. So I think that the 3D seismic data give us very crisp imaging of the deep subsurface. And what we're going to do now is try to match that crispness with this type of helicopter-based EM survey. Now, just so you folks know, that tube and the helicopter, they're not allowed to survey over biochar. The FAA restricts the use of that kind of suspended instrument off of the helicopter from going over any residential areas. So we will work around the community.